So you get the derivatives first, right? So the derivatives, we have to use quotient rule, and then we fully simplify. So I'm just going to give you those fully simplified derivatives right away. So x squared 2x minus 3 all over x minus 1 squared. That's the first derivative. And then the second derivative, fully simplified, is 2x times x squared minus 3x plus 3 all over x minus 1 cubed. Okay, so that's a whole bunch of quotient rules and product rules and algebra, right? So whatever, you have it. Now let's move on. What is the information from F? So recall that this is horizontal and vertical asymptotes, right? So what do we get for vertical asymptotes? So this should be, so both of these should actually be pretty quick. What do we get for vertical asymptotes? Just x equals 1, right? And what do we get for horizontal asymptotes? We needed a couple seconds to figure that one out. What do we get for horizontal asymptotes? Y equals 1? Not quite. So if I look at x going to either plus or minus infinity of this function, doesn't really matter. In both cases, I get an infinity over infinity type limit. So if I use L'Hopital's rule here, I get the limit as x goes to plus minus infinity, and I get 3x squared over 1. And in both cases, I just get plus infinity. So actually, there are no horizontal asymptotes. And we know that on both sides of this graph, it goes up to infinity. Okay. Next, information from first derivative. Okay, and the subtlety that we haven't seen yet is going to actually appear in the first derivative. So even if we don't get to the second derivative, that's okay. So first of all, we make a sign chart. What are our cut points? Zero and one, not quite zero and one. So the first derivative is on the right side of the screen in case you missed it. So let's see, 0 and 3 halves. Not quite 0 and 3 halves. 0, 1, and 3 halves, right? Why is the 1 there? The 0 and 3 halves come from critical points, but the 1 comes from it being a vertical asymptote, right? Don't forget the vertical asymptote. So we actually do get 3 cut points. So x equals 0, x equals 1, and x equals 3 halves. Let me just make sure I have my notes here. Okay. All right, so 0. The 1 is a vertical asymptote, so I'm going to make sure I put that on the sign chart, and then 3 halves. So what do I want to be my my test points? Let's do -1, 1 half, 1.5, so 1.25, and then 2. Okay, so f prime of -1, f prime of 1 half, f prime of 1.25, and f prime of 2. Now, the denominator in the first derivative is squared. So the denominator is not going to affect the sign at all, right? Because the square always gives you a positive number. So I'm just going to look at the numerator. And the numerator also has a square there, right? So I have 2 terms that always give me positive. That's interesting. And this is actually what's going to cause this little subtlety here. So the 2x minus 3, just let's look at that. So 2x minus 3, it switches signs at 1.5. So it should be negative, 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 and then positive. So here, so that means I get negative, 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 and then positive. The only factor that's really causing anything to change sign is the 2x minus 3. Everything else is positive. Negative, 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 positive. So I get decreasing, 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 increasing. So now before we write down our final answer for this part of the problem, are there any questions so far about what we have done? Either what the cut points are or finding these signs or anything like that? So again, I want to emphasize, do not forget x equals 1, right? Do not forget that as a cut point because it's a vertical asymptote. Okay, so let's start writing down these answers. So where do I have decreasing? And what is the correct formatting for the decreasing answer? Negative infinity to 1. Okay. 1, 2, 3 halves, bracket of 3 halves. Okay, so that's what I kind of wrote into the chat. Does anyone else disagree? Does anyone else agree? What do you guys think? Justin, what do you think?
I agree with her.
You agree with her? Thomas wrote negative infinity. So first of all, you can't have a square bracket negative infinity. Negative infinity, 0, square bracket 0. Okay, so Thomas, so we have two separate answers here. So this is what I want to bring up. So first of all, when we have two intervals that match, this goes for concavity also, right? So when you have two intervals that match, if you have decreasing, decreasing, or increasing, increasing, or concave up, right? If you have two of the same thing in a row, you actually have to combine them, right? Because what this really means is, I mean, we have a horizontal tangent line at 0, that's true, but it's decreasing on both sides. And because the function is continuous at 0, it means it's actually just decreasing the whole way through. So for some, writing the two intervals separately like that would be incorrect, right? This would be true if maybe I had a function that kind of maybe looked like this, decreasing and then decreasing, maybe something like that. And I'd have to actually perhaps not combine them. But because the function's actually continuous, I need to combine them into one big interval. Right, because that's actually what's going on here is we're going to see we do have a horizontal tangent line at 0, right? Because x equals 0 was a critical point. But what happens is we have it's decreasing and then it's decreasing. So it kind of looks like a cubic, right? It looks like a saddle point at x equals 0, but it's still decreasing the whole way through. It doesn't stop at 0 or anything like that. So that's the one big subtlety I wanted to make sure that you guys have seen, that if you have two of the same thing in a row, you need to combine them if it makes sense. We do not combine the two across 1 because like Ayana said, it's discontinuous at 1. So you can't combine them. You actually do have to keep that separate because that's a vertical asymptote. Okay. I mean, the rest of this part of the problem is pretty straightforward, right? The increasing then is 3 half to infinity. We have a local min at x equals 3 halves, and we do not have any local maxes. Right. So again, what does this function look like? It's going to look like that. So I know we've discussed saddle points before, but they never actually come up in any of the examples we've done so far. So this is the first time we've seen a saddle point. Okay, so we only have about like 3 minutes left. That's not enough to really finish the problem. We can do a little bit. Yeah, should even. I don't think we can actually finish in 4 minutes. We're gonna get interrupted. So actually we can keep it there. We can end it there. I would encourage you to finish the rest of the problem. At least get the sign chart for the second derivative. So the second derivative is up top. So when you set this equal to 0, I'll tell you the answer. You do get x equals 0. The quadratic gives you no solution. So you're only going to get x equals 0. So you're only going to get 2 cut points for the second derivative. X equals 0, but then you also have x equals 1 because of the vertical asymptote. Sasha asks, is it always a saddle point if there is a critical point between 2 decreasing intervals? Yes, or 2 increasing intervals. Yeah. I mean, that's actually the definition of a saddle point. A saddle point is a point where we have a critical point, but no change in the sign of the derivative. So it just goes increasing, increasing, or decreasing, decreasing. That's actually the definition of saddle point. Okay, so we'll end it there. Maybe we'll finish this